definition for it, I think. Energy makes something go. Any other thoughts on that? Ouch. Made myself bleed. When did that happen? Anyway. Any other thoughts? Energy, what is energy? Turns out that making something go is certainly one way to define energy. Something that moves has to have energy to make it move at some point. Things just don't move on their own. And you could generalize it to say that energy is the stuff that makes everything happen, right? If you want something to happen, any kind of action, any kind of whatever, then energy has to be present to make it happen. Energy is the stuff that allows force to do its thing. Forces have to draw energy from somewhere. They have to have this ability, and that ability is measured by energy. So, we're going to actually study many versions or forms of energy in this chapter and the next, because energy does take many forms. And energy is always switching back and forth and trading itself off for different types of energy. It can convert itself. It can be converted into different kinds of energy, different manifestations of energy. And does that mean that there are different types of energy? It doesn't necessarily mean that. That just means there's different ways of manifesting energy. In other words, energy shows up, or it shows its presence in different ways. Energy is very much a mysterious thing. We understand what it does. We understand how it can be transferred around through the universe, but we don't necessarily understand exactly what it is. What is it that makes energy have this ability to do things? We don't really know that. We're trying to understand that. That's one of the more fundamental, basic studies of physics. And it's being studied by cosmologists and theoretical astrophysicists and all kinds of people trying to figure out. One of the things you've probably heard of before is this idea of dark matter and dark energy. Maybe you've heard those terms before. People that are studying those things are trying to study what energy is. Also people that are trying to study vacuum waves and vacuum fluctuations and things like this, because we know that energy can actually travel through nothing. Energy can travel through space and have absolutely nothing that it does in that space as far as we can tell, except that it travels through it, which is not true of anything else really. Not many other things can do that. I mean, matter can travel through empty space, but then it's not empty space anymore, right? Empty space becomes full of something when there's matter in it. Like if an asteroid travels through empty space, then it's not empty space. There's an asteroid there. But energy can travel through empty space, and it's still empty as far as we can tell. But the energy gets through it somehow. So, I mean, there's lots of mysterious things. People that suppose that scientists understand the universe in its entirety are deceived. It's not true at all. There are many mysteries that we're not aware of, things that we don't understand. In fact, one of the big studies of the universe, one of the big mysteries in the universe is that there seems to be a lot more energy in the universe than we can detect. We have evidence that there's much more energy out there than we can actually see or detect using instruments and the methods that we have. The evidence of the energy is there, but the actual energy we can't see, we can't measure for some reason. So, interesting things. Let's talk about a very simple form of energy. And this very simple form of energy was one that was discovered many, many years ago. It was discovered by physicists and scientists and mathematicians working on work of Newton and Galileo and others. And there were many people that were arguing about what these things were that they were measuring. They didn't really know they didn't really understand what was what. What's velocity versus what's acceleration, for example. Things like these. These things they were still kind of working out. Things that were very obvious to us, they were kind of working out. And one of these things was energy, and another one of them was momentum. They knew that both of these things were quantities that you could measure. You can measure momentum, you can measure energy, but they didn't really know how these things related to other things that they were studying. For example, they didn't know how the energy and the momentum of an object that's moving is related to how far it falls from a height. So if you drop a ball from 100 feet, how is the energy at the bottom related to the height that you drop it? Or how is the momentum related to the height that you drop it? And there was a lot of arguing and back and forth and people trying to figure it out, doing the math, trying to figure out the physics of it. And they eventually figured out that there is this type of energy, and that one of the things they figured out is the momentum and energy are not the same thing. They can be related to each other distantly, like second cousins kind of thing, but they're not related to each other directly in any real way. And so that made kind of this diverging path for the studies of energy and momentum. For those who were studying energy, when they were studying energy, they came up with this type of energy called work, where the work is the type of energy that makes things move, like you were saying. So work is the type of energy that causes something to move. And so it's going to obviously be directly related to force. And it's also going to be related to distance, because to move means that you go through some distance, you travel some distance. And this is the equation for that. And it doesn't make maybe a lot of sense in this form, but if you've started off calculus here, you know that the derivative of something, if you take the full derivative of something, dw, right? That means that what you've done is you've cut it down into little pieces. Have you gotten to that part in your calculus class yet? Where you're doing derivatives?
Last chapter was about derivatives, like we just started talking about.
Okay. So the derivative part of something, if you take the derivative with respect to something, dx dt or something like this, that means you have some function x, or usually in calculus you take the derivative of that function. So you take this function that's time dependent, which in other words means it's changing in time. This function has some kind of movement through time, change in time. When you take the derivative with respect to time, that means that you're looking at how this thing changes in time. And that's fine, that's one thing. However, if you just take the derivative of a function, you just take the full derivative of it, like this, you're not taking it with respect to any particular variable, that means something a little bit different. So in our case, you have the derivative of the work. And that means that the work itself is a total amount of something. So it's a total amount of energy that is being used to move this object, right? When we take the full derivative of it, that means that you've actually broken it down into little pieces. So if this is the whole, then the derivative of it might be little pieces like this. Like you've sliced it up. And each one of these is a dw. It's a little derivative of it. It's a little piece of it. And that's kind of the way that you can think of this complete derivative. And it doesn't have to be slices like that. It can be little cubes, or it can be little spheres, or it can be pie wedges. It's actually how you slice it up is in the details of math. And that's something else that we'll learn later. We'll understand this a little bit later as we do more of this. But the whole idea of this is that you break this down into little pieces and then you put it back together using a mathematical construct called the integral. Right? The derivative means to break down into pieces. Integral means to put it back together. Quite literally. So the integral of the complete derivative of the work, dw, will just equal the work because you're putting it back together. This is absolutely true in every single situation on the planet. Okay, this is an absolute law of it's a law of the theory of calculus. And so what they're saying here in this particular box is that if you break down work into tiny little pieces, these tiny little pieces that we're going to add together eventually, this is what it looks like. It looks like the force vector times a little derivative of the distance. So you have a force that's acting, and you have this little distance that it's being acted on, these little steps, this derivative of the distance, and that's what it looks like. But this multiplication, how do we do multiplication of vectors? Have you done that in calculus yet? Probably not. You'll definitely learn this in calculus at some point. They'll talk about vectors and derivative and multiplication of vectors. Usually in Calc 3, right? Is that where you start learning these? You learn it in Calc 3, but we teach it to you in physics because, once again, we were the ones who remember. So, when you're multiplying vectors together, you have to be very careful because there are a couple of different ways to interpret multiplication of vectors. You can interpret it as just numbers multiplied together, kind of like normal multiplication, 6 times 5 is 30. But remember that vectors can have multiple dimensions. Your force vector can have an x component, a y component, and a z component, right? And your displacement vector r, where you're going to, can also have x component, y component, z component. So do you multiply the x components together, or do you multiply the y ones together, or do you multiply them all together? How do you do this? How do you do this multiplication? Well, there are different types of multiplication for vectors in different situations. In this particular situation, we're going to be using a vector product called the dot product, which is why we use a dot in between them. So this is called the dot product. And the dot product is the easier of the two multiplications that we commonly use for vectors. The dot product is really quite simple. This is what it looks like. The dot product between two vectors, you take the x component of each vector. So if your dr is just a rectangular thing, so in this case you're breaking this into little cubes, three-dimensional cubes. So if your dr vector is just a dx plus dy plus dz, and your force vector is just an f of x plus f of y plus f of z, and they all, x hat, y hat, z hat, then you just like in general. Here's your force vector f. It equals fx, x hat, or I hat, plus fy, j hat, plus fz, k hat. And your r vector, or your dr vector looks like this. It looks like I hat plus j hat plus k hat. Right? It's a unit vector that is sorry, no, it actually wouldn't. It would be dx. So dx I hat, dy j hat, dz. So you've got each one of these things, and this is not a unit vector. It's actually just some vector, but it has components of derivative components, right? dx, dy, dz. I hat, j hat, k hat. If you take the f vector, and do the dot product with the dr vector, then you take this component and this component, the x component, to multiply them together, f of x times dx. And then you add it to f of y, dy. And then you add that f of z, dz. Notice that I don't have any I hat, j hat, k hat down here. The product of two vectors, when you use the dot product, always ends up as a scalar. It ends up as just a number. You're just going to get a number out of this. You're not going to have any vectors, you're not any components and unit vectors or anything like that. It just comes out as a number. These are just three sets of two numbers each, multiplied together and then added together. Now, this may seem a little confusing right now, and it certainly is, but the good news is that when you do it in practice, it's not all that hard. It's not, when you actually have numbers and things like that to deal with, it's not all that difficult. Now another representation of this dot product here is you take the force vector itself and take its magnitude, and then you take the r vector and you take its magnitude, and you multiply them together. Right? Well, what's the magnitude of a vector? The magnitude of a vector is you have the Pythagorean theorem to help you with that, right? You take the x component squared plus the y component squared plus the z component squared, take the square root of that, and you can get the magnitude. And you can do it that way as well, but when you do that, you have to multiply by the cosine of the angle theta between the two vectors, which is a little more complicated to get. You can get it. There is a formula for this earlier on in chapter 1 or 2, I can't remember which. So you can definitely get that cosine of the angle between the two vectors, but it's more challenging. So it's actually much easier to use this method. This method, you don't have to have the angle between them. It already accounts for the angle between them. Right? However, if they tell you the magnitudes of the vectors and they tell you the angle between them, maybe this one's faster. In the end, once you've done that dot product, you do have to still take an integral over the path that the particle follows, because the path matters. If the path is a curved line between A and B, the work done is going to be different than if it's a straight line between A and B. In other words, what's the way to say this? The path determines the energy. The path is in part responsible for the energy expended, and that can be for many reasons. It can be maybe more resistance on a longer path. It could actually mean the path is going around a hill, so it makes it actually easier to move it, right? It may be that the path is going up over a hill, so it makes it harder to move it, or whatever. But the path matters. The path is going to affect not only the distance that you have to travel, but the force itself might be dependent on the path. The force might have to change depending on the path that you take. And so in this case, the force and the path can be functions. They can be functions of time. They can be functions of distance or whatever. And that's just real life. So this equation becomes really quite general. It can be used in just about any situation without having to modify it or add to it, as long as your force and your displacement vectors are true displacement and force vectors. They tell you exactly what's going on in the real world. You can get the exact energy needed. Now, of course, that's very difficult to do. Especially when we're starting off here, we want to have very simple things, to multiply together in here, and very simple integrals so that we can actually do the math. And that's fine. So in the end, we might end up with something very simple, like a constant force in a straight line. If you have a constant force in an integral, what happens to constants in integrals? They come out of the integral, right? Now, since this is a vector that's in a dot product with dr, we'll do the dot product first. So we go ahead and do the dot product, and we get f of x dx, f of y di, f of z dz all added together. And each one of these we can separate into its own integral, which is the antiderivative. It just does the opposite of the derivative, to remember that. And so what we can do is we can actually do each of these separately. This integral, this integral, and this integral separately, and then add them together. And when we do that, we have an f of an x and a dx, and the f of x can come through the integral, because constants just come out of integrals. Why do constants come out of integrals? Remember, the integral puts the pieces back together, right? So if there's something in here that's in pieces, like dw, because we already said that that's like something broken into pieces, then it has to be put together. But if there's something multiplied in front of it, like 5 doesn't need to be put back together. 5 is just already put together. So it can just come through the integral, and the 5 can stay outside, and all you have to do is put this together. So that's the idea there. In this case, the force is a constant. The force isn't changing in any direction as we push our lawnmower down here. And so the force can come out of each of these integrals, come out in front of each of these integrals like this. And how does the remaining part of the integral will get completed. What an integral does is it, in its simplest interpretation, is it tells you, what it does is it takes the final value of x. So here's the beginning of the path, here's the end of the path. A is where you start, B is where we end. It takes the value of x at B, and then it subtracts the value of x at A. It takes the ending value and subtracts the beginning value on each of these. So for the first one, you get f of x times x at B minus x at A. And the same thing for the y. You have force in the y direction times y at B minus y at A. And the same thing for z. And in the end, what you get is f dot rb minus ra. This is kind of the end result of this, as long as you have a constant force in every direction. The force doesn't change in any direction, right? And you have a very easily definable path in x, y, and z. This is all general work, but in practice, what this means is if we push in a straight line, if our lawnmower is moving in a straight line, and we have some force that's constant, then that whole equation breaks down to this: work equals force times distance times cosine of theta. Where the force is constant both in its direction and in its magnitude, the distance is whatever distance the thing moves, and the angle theta is the angle between the force applied and the distance moved. So it becomes a very simple equation. So here is the work being done. So a person, when you push on a lawnmower, you're pushing down the handle. So the force actually has to transmit through the handle. So whatever the angle the handle is the angle of the force that's being applied to the lawnmower. This person is pushing downward on the lawnmower and forward on the lawnmower. And then the lawnmower moves forward. So you have the angle theta here, and the cosine of the angle theta, actually times the force, will tell you how much of the force is actually pointing in the direction of D. It's what we call a projection. So when you're studying calculus, you will hear the word projection used for the dot product. So a dot product gives you the projection of one vector onto another vector. So in this case, it tells you how much of this force that the person is pushing with is actually force that is pushing the lawnmower in the direction that it's actually moving. And then you have f cosine theta times d, and it ends up being fd cosine theta. It's that simple. What happens if you have a situation like this, where you have this lady who's standing here holding this briefcase up by applying a force upward of f, and then the lady is walking forward some distance d like this, lifting that briefcase up with this force upward. Well, you have the upward force that's straight up and the distance force, which is horizontal to it, or horizontal this way. So what is fd cosine theta going to equal? Well, cosine theta is the cosine of 90, and the cosine of 90 is 0. So fd cosine theta is going to equal 0. So how much work does this lady do to lift her briefcase while she's walking? None. There's no work being done, no energy being expended in the form of work. It doesn't mean it doesn't have any energy being expended. It's just not being expended in the form of work. In other words, none of the energy that she's lifting up with is going into moving the briefcase. Now, some of the energy in her feet as she walks forward is making the briefcase move forward. So some of that energy is going into work, but that's a different force. So it's a different situation. Excuse me. And people get kind of confused by this. They say, if there's no work being done, why do I get tired? I get tired because I'm losing energy. If there's no work being done, where does that energy go? Right? Well, that energy is it's turning into heat. Your body is essentially, you're holding up this briefcase, and as your body is going through all its biochemical processes to keep your muscles tensed and your fingers clenched and all these things, they release heat. And that heat is another form of energy. And that's where the energy is going as you're trying to keep your hand closed and your muscles tight to hold up that briefcase. that energy is not going into moving the briefcase. What's going into moving the briefcase is the energy in your feet that is pushing the briefcase forward. It doesn't mean energy is not being expended. Energy is definitely being expended holding that briefcase up. But it's just not energy that's turning into movement. Work energy always turns into movement. It always creates movement. Okay? Other types of energy do other kinds of things. So, this is work being done on the briefcase. Now, another thing that's important to recognize about work is that work can be positive or negative. Okay? Work is not a vector, so it doesn't have direction. And no kind of energy is a vector, so no kind of energy has direction. However, many kinds of energy can be positive or negative depending on where they're going. So when we're dealing with energies, you have to think is, what is my system of interest? What is the system that I want to know about? In this case, with the briefcase, it might be the briefcase. So you say, how much work is being done on the briefcase with the hand? Well, in this case, we calculated that and it was 0. In other words, none of the movement of the briefcase was because of the hand moving it forward. And so no energy was put into the briefcase. The briefcase didn't gain any energy, in other words, from the hand. However, the briefcase did gain energy from the feet moving forward. The feet pushing her forward and pushing the briefcase forward with her. So the briefcase did gain some energy from the feet because the briefcase went from sitting still to moving forward. And that's a gain in energy because it's now moving. The work that caused that movement would be the force by the feet that caused the briefcase to move forward times the distance that the briefcase moved. That would be the work done by the feet on the briefcase. So that amount of energy was added to the briefcase, and now the briefcase has this kind of movement energy to it, done by that work added to it. Right? But when I was talking about negative work, what can you imagine could do negative work? What kind of work can cause movement from a force and take energy out of something? Let me give you an example. Let's say that this lady is walking along and then she throws her briefcase along the ground, like she's bowling her briefcase or something. And it slides, and then eventually what happens? Eventually it stops. Right? Was there work being done on that briefcase while it was sliding? Yeah. What was doing the work? What was causing the movement? Let's say after she threw it. So her throwing it definitely gave it some energy, but then it slowly slid to a stop, right? What caused it? What caused that change in movement? Because stopping is a change in movement just like going is change in movement, right? Friction. But did friction give energy to the briefcase? No, it took it away. It actually took away movement energy. And so in that case, the friction is doing negative work on the briefcase. Okay? And in fact, when the woman starts to walk forward, the briefcase does negative work on the woman. The woman would be going faster with that same force in her feet if she wasn't carrying the briefcase. So while the woman does work on the briefcase does negative work on the woman. Like she slows her down a little bit. Keeps her from going the full speed she could be going, right? And friction definitely slows things down. So work is just one form of energy. It's that energy that causes movement over a distance. So if we calculate the work to do pushing the lawnmower, and we have a 35-degree angle with a force of 75 newtons, and we move this thing 25 meters, we do work of force times distance times cosine of angle. We plug in those numbers, and we get 1.454 times 10 to the 3 Newton meters. So 1,500 Newton meters, which we call joules, named after, I can't remember his first name, but some French guy. Anyway, so joules is the unit that we use for Newton meters for energy and work. Of the lawnmower for 75 or for of 75 newtons of force for 25 meters with a handle angle of 35 degrees gives us 1.54 10 to the 3 joules. How many joules is that? Well, how much energy is that? It turns out it's not very much. That is about a third of a, yeah, it's about a third of a food calorie. So, you know, you eat your breakfast and you eat 400 calories for breakfast or something. Most people eat about 400 or 500 calories for breakfast. And one third of one of those calories is how much energy you expend in getting that lawnmower to move. That's how much energy is required to actually make the lawnmower move. It's not how much energy you burn making the lawnmower move. Why not? Humans that will actually burn 10 times that to push this lawnmower this far. Why? Yeah, your body's not very efficient at turning chemical energy into kinetic energy, or chemical energy into movement energy, or kinetic energy into work, right? Chemical energy has to go through processes. There's heat lost in the chemical processes. There's friction within your muscles and your bones. All that friction is energy that is lost in your body in heat, you know, for the most part. There's lots of things that there's products in the chemical reaction that have to be created. You have the original things that you start with in a chemical reaction. They come together, they trade electrons, they release some heat, they absorb some heat, they do some other things, and they create these products. Well, those products have to leave the body. The products have to go into other things, and usually what happens is the products leave the body because most of the products are like water and carbon dioxide. That's pretty much the products of all chemical reactions in the body. And these products have to leave your body with breathing, and so your lungs have to work, and they have to burn energy, and everything else has to burn, and all these different things happen. And in the end, you end up burning far more energy than you need to actually do this work, right? Which is fine. But in the end, you're going to you might burn 1/6 of a gram of fat, right? So 1/6 of a gram, 6 times 60, that's 1/100th of a pound. It's not that much weight. All right, so anyway, the word here is an equation for the work done by friction. Of course, friction is always in the opposite direction of movement, isn't it? So the angle between friction and movement is always 180 degrees. Therefore, the cosine of the angle is always going to equal -1. So friction always ends up being the frictional times the distance, the negative the friction times the distance. So that's really quite easy, as long as it's a constant friction going over a distance. So here's an example where we move a couch in the living room. There's a normal force on the couch of 1 kilonewton, and the coefficient of friction is 0.6. We push the couch 3 meters parallel to the wall, so we push it this way, and then 1 meter this way. And we want to know how much work is done by frictional force. And then we don't like its position where we put it, so we move it straight back this way across the diagonal here. And so what we want to do is figure out how much work we have to do to go this way and then this way compared to how much work we have to do to go this way, right? To just cut the corner. And so what they do is they do this work in 2 different dimensions. Remember when we broke this up, we got force times distance in each dimension separately, right? So if we do it in the x dimension and then the y dimension separately, then we get 2 amounts of work being done. And so for part A, you get the 3 meters in one dimension and then the 1 meter in the other dimension. But it's the same coefficient of friction, it turns out, and so you end up with the same amount of work being done. And here we're setting the work equal to the friction. Why? Well, because the friction is the amount, that's the energy we have to overcome to slide this couch. That's the force that we have to push against. So we have to apply the same amount of force as the friction, right? So we use the normal force times the coefficient of friction times the distance that we travel, the 3 meters plus the 1 meters. And we lose 2.4 kilojoules of energy in friction, which means that's how much kinetic energy we gave it to overcome that friction, right? So we see something interesting here. We see that the work that we do to move something at a constant speed against friction is equal to the amount of friction that we have to fight through, right? And that's kind of interesting. However, if we go across the hypotenuse, if we cut the corner on the way back, then it's the friction that we go through times the distance that we travel, which is actually the, we use the Pythagorean theorem to do that. So here they actually do the Pythagorean theorem plus these other two. So if we erase the 3 plus 1 and we just multiply by the Pythagorean theorem, which is the 3 squared plus 1 squared, which is square root of 10, right? So then you get square root of 10. It turns out that the work to go across this is actually smaller than the work to go this way than this way, which you would expect. But the total work done would be the work to get to here, then to here, then back to here. So the total work would be 4.3 kilojoules that you had to do. This is the work that friction did. And when we did the opposite amount, we did 2.4. We gave it 2.4 kilojoules to overcome the 2.4 kilojoules taken out by friction. And then this is the amount of work we did to get it all the way around the whole triangle. So it's very important to think about, if you want to think about the sign, is it positive or negative work? You have to think about the object. For the couch, friction does negative work on objects because it always takes energy out of an object. So friction did negative 2.4 kilojoules of work on the couch, while we did 2.4 kilojoules on the work to move the couch against the friction. The total amount of work done by us on the couch, which was part B, was the 2.4 from going across and up, and then the square root 10, and all of those things multiplied, sorry, not the 2.4, the 3 plus 1 to move it across and then up, and then the square root 10 to move it back, all multiplied by this to get 4.3. Now, in this next part, they're going to talk about what happens if the friction is not constant. What if that force can't be pulled out of the equation? Well, then we're going to have to do some trickier math, and we'll come back to that next time. So, go ahead and get started on your homework there. Let's see. Yeah, I will add some problems to it right now. What I'm going to add to it is I'm going to add some problems that don't require any calculus. That's the first thing I'm going to add to it. So you should be able to get started on those. And most of the problems in this chapter will not require calculus, but we will definitely do some that will require some.